Hi everyone, welcome to another video for research design and analysis. In today's video, we're going to be talking about the bivariate correlation, kind of introducing conceptually what this is, and then at least one formula for a means of calculating the correlation. So what is a bivariate correlation? Well, broadly, it's just a measure of how two variables are related to one another. And correlation, in the statistical sense, is approximately equal to what we would think of as an association in everyday usage, right? This is going to be a little bit more formal because there's actually mathematics behind the calculation of a correlation coefficient that will tell us about how strong that association is or certain elements of the association. And there are different, types of associations that we could measure that require slightly different correlation coefficients. But at its broadest level, right, the correlation is a measure of the association between two variables. Now, some of these might be pretty straightforward things, right? Like how are height and weight associated? And we might have a really strong understanding of how that is just from our observations of the world around us. But there's also going to be other things that are maybe a little more subtle that we could measure with a correlation. So for instance, is self-esteem related to the likelihood of relapse in a sociological study of drug use? Is stress related to performance and kind of human ergonomics and human performance data? There's lots of different things that we could measure, and the variables could take kind of different properties and qualities. What we're going to focus on today is when we have continuous interval or ratio data, and we're trying to look at the association between those variables. So as one example, though, to get us started, just kind of conceptually with what a correlation is and some of the problems that we face when we're calculating correlations, let's think about the relationship between water depth and shark attacks. So this is based on some real data from several years ago, but in the Pacific Ocean, there's a strong negative correlation between the number of shark attacks and water depth. And that's also slightly divided up by, what the different activities people are doing when there are shark attacks. But here you can see kind of attacks, broadly defined as any encounter where a shark, I think bumps to bites somebody as a function of the water depth. And you can see when the water depth in fathoms is much lower, then we have a greater incidence of shark attacks that falls off pretty significantly as the water depth gets deeper and deeper. So, right, if we see that there are fewer shark attacks at greater depth, there's lots of different interpretations that would potentially explain why this relationship exists. One of them, perhaps the most obvious one, but also not a great one, is that shallow water causes shark attacks. This would be a causal interpretation of this relationship, right? And the idea behind the causal relationship would be if I took the same shark and I put it in more water, it's less likely to attack somebody. But if I put that shark in less water, now it's becoming more likely to attack somebody. So in this view of the correlation, we're interpreting it as causal. And that is going to be incorrect, right? The correlation is not incorrect. The correlation is just the association between those variables. So empirically, the pattern in the data is right. The problem is in how we're interpreting it. And our interpretation of that pattern is wrong, right? So this is an important lesson, right, to demonstrate that the correlation is merely a statistic and causation is actually established through our design. And there are different ways that you can try to establish causation. The probably most basic one in the biomedical literature is to use randomized controlled trials, but there are other ways of getting at that. And even in randomized controlled trials, there's confounding factors that make establishing causation difficult. But let's just think about this observational case for a second. So again, we know that there's a negative relationship between water depth and shark attacks. And as we said, that association is real. That pattern of the data is right. It's just the causal interpretation of it that is wrong. And why is it wrong? Well, for one thing, there's going to be this mitigating third variable here, which is the number of people in the water, right? So does shallow water cause shark attacks? No. The issue is that when the water is more shallow, there's a greater people to shark ratio, and therefore the incidence of shark attacks is higher, right? Not many people are out at 16 to 20 fathoms deep in the ocean, but a lot of people are near the beach and on the shore in that sort of 1 to 3 fathoms range. So this is a third variable then that kind of undermines that causal interpretation of the relationship between water depth and attacks. And obviously, here I'm using a kind of ludicrous example where I would hope that that's relatively obvious that the causal interpretation is wrong, but it's something that we need to keep in mind in your research, because you might have a plausible biological reason for believing that this correlation is causal, but if you have purely observational data and you're not taking these other third variables into account, then you're going to make the wrong conclusion. And it's important to not interpret these correlations that we observe causally, because they are just associations. Now, in a later video, we'll also talk about how, it's correlation is not causation, but anytime you have a causal relationship, things also will be correlated. So not all correlations are causations, but anything that's causal is going to be correlated. So we'll talk a little bit more about that in another video. But again, right, we're just introducing the concept of the correlation, where we're going to be measuring these associations and then attempting to quantify them in a statistical sense. So now, what is the correlation then? So association, right, is our kind of common language usage. But what is an actual correlation coefficient? Well, the first thing you need to know is that there is not just one correlation coefficient, there are multiple. So correlation coefficients are a family of related statistics that measure both the strength and direction of an association, and they range from +1 to -1. So a negative correlation, right, between y and x would look something like this, depending on the correlation coefficient you're calculating. But basically, there is a perfectly linear relationship between these two, and as x increases, y decreases. So this is a perfectly negative correlation at -1. The reverse is true over here, right? We have y changing perfectly linearly as a function of x, and therefore this is a perfect positive correlation with an r equal to +1. So we're going to be focusing on what's known as the Pearson correlation coefficient here, where we're assuming that two normally distributed interval ratio data, two normally distributed variables of interval ratio data are being correlated with each other. So there are other correlation coefficients that we can use with like different types of data or different types of relationships, but this is the Pearson correlation coefficient is the most common one, and I think it's a very useful starting point for understanding correlation. And here we have a nice graphic that kind of summarizes how the correlation coefficient measures both the strength and the direction of the relationship. So in this top row, right, we can see we have a perfectly positive relationship. Now, the actual sort of strength of the relationship stays the same in terms of the line that would fit through this cloud of points, but you can see that the relationship isn't as strong. There's more variability in where the data points fall, and that causes the correlation coefficient to go down, right? And then that relationship gets weaker and weaker until eventually there is no relationship, and then we shift into a negative direction. Right, and you can see again that as these data points, the slope of the line that fits through here is the same as the slope that fits through here, is the same as the slope that fits through here, but the strength of that correlation is increasing as the relationship between the two variables gets tighter and tighter. Now, the slightly tricky thing about this, though, is that if you have a perfect relationship, then the actual kind of magnitude of that association is confounded with how tightly the data fit to the line, right? So in this second row, we have a series of perfect Pearson correlation coefficients. Even though here the relationship is stronger, right? It's a greater magnitude, a steeper slope than it is here. But in both cases, the association is perfectly linear. So we're going to have a relationship of 1. If I know what your score is on X, I know exactly what your score is on Y. And the only place that that's going to break down is when this is perfectly flat, because now for any given value of X, I would make the same prediction about what your Y value is, so there's no correlation here. But again, once that slope becomes non-zero, even if it's small, if the relationship is perfect, it's going to be -1 all the way across here. And then finally, in the third row, all we're seeing is that this Pearson correlation coefficient is only or I shouldn't say it's only useful, but it can only really capture linear relationships, right? And if I have things that are clearly related, like here there's kind of a sinusoidal relationship between X and Y, or here there is like a topological relationship where certain values of x do not have values of y in certain spaces, right? And then into really complicated types of relationships. These all would have correlation coefficients of 0. There's clearly a pattern there, right? There's some relationship between x and y. That's not just random, but we're not going to detect it with our correlation coefficient because the Pearson correlation coefficient measures linear relationships between two variables. All right, so let's contextualize this in kind of a health and physiology example. So there's a really strong association between your ventilatory capacity, measured as your VO2 max, and the time in which you can run the 800 meters. So again, we're thinking about this as an association, and we're going to try to take these data, which we know are associated, and calculate an actual correlation coefficient, which will statistically capture the direction and strength of that association. Okay, so here are our data again, and then here they are plotted, right? So it's a little bit easier to see, but we've got your 800 meter time on the y-axis, we've got your VO2 max on the x-axis, and you can see that there's generally a negative relationship in these data, and it looks pretty strong. Like these data are pretty tightly clustered together. So for every 1 point increase we get in your VO2 max, it's pretty likely that your 800 meter time is going to get faster, right? The time is going to go down, so you're running more quickly the fitter you are. So now how do we calculate a correlation coefficient here? Well, the Pearson correlation coefficient actually relies on the z-scores between those two variables. So we can think about, our correlation coefficient R is the sum of each z transformed x times each z transformed y divided by the total number of observations minus 1. And so again, if you think about our x is our VO2 max, our y is the time in the 800 meter dash, the z-scores will tell us, are you above or below the mean? So when things are positively related, you'd have a positive z-score on x being multiplied by a positive z-score on y. When things are negatively related, as in our VO2 max example, right, someone who is well above the mean on VO2 max is going to have a positive z-score. But they're going to be much faster than the average person. So their 800 meter time is going to be below the mean, and they'll have a negative z-score. So I'm going to have positive numbers getting multiplied by negative numbers to ultimately get a negative result. And then I'm going to be adding all those things together. So if on balance this becomes very negative in the numerator, I'm going to end up with a negative correlation coefficient over here, and it will present a negative relationship. And the more tightly these z-scores are related, the closer and closer this R value is going to get to 1. So computationally, we can also rewrite this a little bit differently, right? If we don't do the z transform first, we could actually think about it as the sum of each x minus the mean of x divided by the standard deviation multiplied by the corresponding y value minus the average y value divided by the standard deviation of y. So this is the same formula, right? It's just down below. I haven't transformed these things into z-scores, and I'm leaving them in kind of their raw units to make the computation a little more clear. Now, conceptually, another way to rewrite this formula that I think helps is we can actually separate the z-scores out again into kind of each x minus its mean divided by its standard deviation, but we can kind of crunch this formula together. And what I think this helps to show is that the correlation coefficient is a measure of how much x and y vary together, right? Do positive deviates on x go with positive deviates on y? Or do positive deviates on x go with negative deviates on y? So the numerator here is a measure of how much x and y vary together. And then what we're dividing by is the degree to which x and y vary separately, because the standard deviation of x by itself is down here, and the standard deviation of y by itself is down here. So if r is big, whether it's positive or negative, then x and y vary together more than they vary separately. If r is small, then x and y vary together less than they vary separately. And at some point, right, they won't vary together at all, and that would give us a correlation coefficient of 0. So we can actually do this calculation in our VO2 max data. So, you could do this by hand if you want to follow along, or you can just trust that I've done the math correctly here, right? But what I've done is I've taken our VO2 max scores and our time scores. I've pulled out the mean and the standard deviation for each, and then I've transformed each of these observations into the corresponding z-score. So like for this first one, if I do 52.5 minus the mean VO2 max, right, which was 62.7, this is less than the mean, so we know that this should be negative, right? So I take that difference, I divide it by the standard deviation of 6.3, and it does in fact work out to be a negative, 1.62. And then I just do that calculation for all the VO2 maxes. I do that calculation for all of the time variables, and then I can multiply those z-scores together to get the z-score product, right? And you can see then that I have this collection of z-scores multiplied together. Finally then, I had to take the sum of those z-scores and divide it by n minus 1, and what I end up with is an r value equal to negative 0.78. So again, remember that our correlation coefficients can only get as big as negative 1. So a negative 0.78 is actually a pretty strong relationship. And that fits with what we saw kind of just in our qualitative inspection of this graph. We said this looked like a strong negative relationship. Our calculation of the R value confirms that and actually gives us a precise number of just how strongly negative this relationship is. So that's always a good thing to check. Look at your data first, right? And then if your statistic doesn't actually match, right? Like if this was suddenly positive, then I'd have to worry and say, uh-oh, I think I made a mistake in my math somewhere. Something is wrong. If I looked at it and I said this relationship is negative, and then my answer turned out to be positive, that should throw up some red flags, and I probably want to go back and double check my calculation. But in this case, I know it works because I double checked it, but also it fits with the qualitative interpretation of the data. The other thing that we can get is this r squared value, which is quite literally just taking the r value and then squaring it, and that becomes 0.609. And this r squared value is also very important. So r is our correlation coefficient, but r squared is what is sometimes referred to as the coefficient of determination, or also the explained variance. And what that means is 61%, because it's 60.9, but about 61% of the variance in 800 meter times is being explained by your VO2 max. So these are two ways of understanding the strength of that relationship, right? The correlation coefficient tells us about the direction and kind of how strong the prediction is between those two variables. The r squared value tells us the proportion of the variance in the y variable that is being explained by the x variable. And we'll get into more detail about the calculation of this r squared and exactly what that means in one of the other videos in this module. But hopefully this gives you a good introduction to the Pearson correlation coefficient, and we're going to build on this as we extend correlation into regression and then into multiple regression and kind of higher level statistical concepts.